Hello everyone and welcome to my new session on operating system. So this is the fourth session of operating system. So I have already covered topics like introduction to operating system, process management and threads in my previous three sessions. So do watch those sessions if you have not watched already. So the link to the playlist of those videos should be there in the description here of this video. So do watch those videos also, like, to gain more knowledge about operating system. So this is the fourth session of the operating system, and here I'm going to discuss about process scheduling. And also do not forget to subscribe to my channel for more updates. Okay, so this is regarding the previous session. So in the previous session, I covered about thread management. So I covered about inter-process communication. Then I covered about introduction to threads, what is the difference between process and thread, difference between multi-processing and multi-threading, and what are the challenges in while you write multi-threading code, what are the challenges that are faced. So these all topics I covered in my previous session. So of course watch all my previous operating system sessions by visiting the playlist link in the description. That should be there in the description. And this session may be long because I also have to explain the process scheduling algorithms by taking examples. So this video may be long, but I have actually broken down the video into different timelines so that you can see in the description. So if you want to jump to some process scheduling algorithm directly, you can use the description timeline and jump there. And also, of course, subscribe to my channel for further updates and keep supporting me. So what's the agenda for this video? So for this session, the agenda is that first I will cover the difference between IO bound process and CPU bound process. Then we will look at types of scheduling queues and types of schedulers. Then we'll move on to the difference between preemptive and non-preemptive scheduling. Then what is the role of dispatcher? What is context switch? What are the scheduling criteria in operating system? Then what are the scheduling algorithms like FCFS, SJF, SRTF, priority scheduling, round robin? I will tell you the advantage, disadvantage of each of them, and also I will basically solve a numerical here, like give you an example of this, how it works. And at last, I will also cover multi-level queue scheduling. So these all I will cover in this session. Now, as I always do, I always give you the possible interview questions that can be asked from particular topic. So from process scheduling, these questions can be asked. Even in your college exams or interviews anyway. So what are different scheduling criteria? Why is it important for the scheduler to distinguish IO bound programs from CPU bound programs? Difference between short term, medium term and long term scheduler. What is context switch and a dispatcher? What is the difference between preemptive and non-preemptive scheduling? What is convoy effect in operating system? Then what is aging in operating system? Then how to implement FCFS, SJF, SRTF, priority or round robin scheduling. So I will just tell you the example, but I am not going to tell you the code here. But I do have written codes for them. So do find the, if you want to like how to implement it using C++ programming, do find the links to those videos in the description. Then what is starvation in process scheduling? What are the disadvantages of each process scheduling algorithm? And at last, what is waiting time, turnaround time, response time in process scheduling? So you should be able to answer all of these questions once you go through this session. Now let's start this session. So the first part is like, what is the need for process scheduling? So why do we need process scheduling? So in some cases, we do not have, the scheduler, or I will say scheduler does not have a choice. So let's say if a process terminates, you do have to schedule some other process. And let's say if the process undergoes IO also, the CPU is empty, right? If some processes are there, you need to schedule them. So there are no choices here. But in some cases, choices are there, but still you need process scheduling because you need to increase the response time of the process and also increase the CPU utilization. So for these two, you may also forcibly remove some process from the CPU and schedule some other process in this case. So that's the need for process scheduling. Now let's try to differentiate between what is IO bound process and what is CPU bound or processor bound process. So IO bound processor, as you can see from the name, they are IO bound. You will think in the mind that it should be some process which undergoes a lot of IO. Actually, that's what actually it means. That means process spends most of its time waiting for it or waiting on IO, input output. So this process, what they do is they usually run for a short time and then again undergoes IO. That is blocks on IO. So this IO can be here network IO, disk IO, keyboard IO. It can be anything. So typical examples of this type of applications which are IO bound are most of the graphical user interface applications. So what they do is, okay, you will think that this graphical user interface, they are not reading or writing, I mean, much to the disk, right? Still, if you think about this, I mean, these applications, GUI applications, they keep on waiting for the user input most of the time. So that's also IO, kind of IO, because they are waiting for the keyboard input, and keyboard is a kind of input device if you see. So basically, they are waiting for some IO here. So most of the, I mean, text editors, if you see, they keep on waiting for your input. Terminals also, and also there are multiple processes which, if they write or read heavy from the disk, I mean, they do heavy reading and writing from the disk. They also can be categorized into IO bound process. Now CPU bound process is quite opposite of this. So this CPU bound process spend most of their time in executing code. That means they are mostly on the CPU running some code, and they will run till they are preempted by the, I mean, kernel. Till then they will keep on running. So a simple example will be, if you run this code in finite while loop, so this will keep on running on the CPU, right? Unless it is preempted, it will keep on running. So this is a very good example of CPU bound process. Other examples could be like programs that does a lot of mathematical calculations, like games. So when you are doing mathematical calculations, I will say CPU is executing some instructions, right, for calculating those numbers and results. And in programming, I mean, in programs like games and most of the games that you play, a lot of mathematical calculation happens for the rendering of graphics. So I will say these are one of the examples of CPU bound process. Now, some process can be both. They can be both CPU bound as well as IO bound. So take example of text editor. So they are mostly waiting for the input from the user, but once they get the input, they start doing the spell checking, right? So this spell checking is a CPU bound. I mean, if you see, spell checking will be done by some code, right? So that is CPU bound, but it's waiting for input is kind of IO. So it's a combination of both. Similarly, games also, if you see, I mean, they are waiting for, if you are playing with mouse or joystick or anything, so those are input, right? So they are mostly waiting for input. But when you give their input, and of course they have to also render the graphics also. For graphics generation, they will also, this is CPU bound, this part. But this waiting for input is again IO part. So some process can be combination of both. Actually, most processes are combination of both. Now it depends on like what that process is doing. Is that process spending most of their time in IO or most of their time in CPU? And I will say this is very useful for, I mean, scheduling, because the kernel should always try to, I like have a mixture of both of this type of process. Let's say if you have only, let's say if the kernel keeps on scheduling only IO process, let's say, then what will happen? You see the IO process will mostly use the disk and other input output device. So this output device will be busy all the time, but your CPU will be idle most of the time because it's the IO process. Now let's say if you have only CPU bound process, in this case CPU will always be busy, right? But your input output device, right, will always be, I mean, idle. So that's why the kernel needs to schedule like a combination of both of these type of process regularly, so that both of these, like your input output device as well as your CPU, both are utilized most of the time. To increase the utilization of both, the kernel needs to pick up like a combination of both of this type of process. Now let's look into schedulers, like how many schedulers we have, and also schedulers are closely related to scheduling queues. So both you will understand from this. So I will tell you a typical example. Let me clear this, and I will give you a very good example to make you understand this before I go into the theory part. So in the old times, when you had batch operating system, what used to happen is, so there used to be jobs or tasks, and what will happen is, first all these jobs will be stored on the disk. So they are, let's say, stored here on the disk. Now this is actually a queue here on the disk that is called job queue, right? Now what will happen? I mean, there is a scheduler associated with job queue, that is long-term scheduler. So what will happen? See, you have your RAM here, but normally your RAM will not be like the size of the disk. It will be very small. And what can happen is, not all these jobs that you have, they cannot be directly, all these jobs cannot be bought, I mean brought to this RAM at the same time. So what this long-term scheduler will do is, it will pick some tasks from this. Let's say it pick this one, and this one, and it will basically bring this to the main memory or to the job queue. That's what. Okay, sorry, not job queue, ready queue. I will discuss ready queue. What is the ready queue? So it will basically, there is a ready queue here. Now what it will do is, it will load like all these programs into the main memory, and also as I told you, process control block will be created for each process. That is the data, I mean data type for this, I mean process. So in the ready queue, also PCB will be created by the kernel for each of these process. So let's say this is PCB for 1, PCB for 2, PCB for 3, and these all PCB are stored in the ready queue, right? Now ready queue is basically for, like, okay, all the processes are there in the memory, but these processes are waiting for the CPU. Those processes which are, I mean, there in the main memory but waiting for the CPU are kept in the ready queue. Now the scheduler actually only deals with this ready queue. This is also called actually this is called ready queue, and this scheduler will now pick the task, I mean processes from this ready queue, and schedule it on the CPU. Now you got my point, right? So this is a job queue that is there on the disk, and long-term scheduler is associated with this. Then you have a ready queue. This is the main memory, and here you have the process which are waiting for the CPU, and this scheduling is done by the short-term scheduler. I forgot this. This is also called CPU scheduler. So this actually does this task of picking the task from ready queue and scheduling it on the CPU. So now you understood what is short-term and long-term scheduler, right? Now, okay, now understand this. Okay, I will just go to the theory here. So long-term scheduler load task from the job queue to the main memory, that is ready queue. So it loads into the main memory, but then PCB for each process will be created, and they are there in the ready queue. So this is mostly used in batch operating system, not in the time sharing operating system. Not any, today most of the operating system are time sharing. So long-term scheduler is not used much, and this does not run very frequently. Of course, you know why? Because it has loaded like 5 or 6 tasks in the main memory. Now these 5-6 tasks should complete, then only this long-term scheduler will again run, right? But think about short-term scheduler. This is also called the CPU scheduler. This schedules process present in the ready queue on the CPU, but this runs very frequently, because if, let's say, the time sharing operating system, and if you are using round robin scheduling algorithm that I will discuss later, then you need to keep rotating this process, right? Give some time slice, remove again, give some time slice, again remove again. That's why this keeps on running frequently, and this also needs to be very fast. The last one is medium term scheduler. So this is also called memory manager, and this is not related to process scheduling. So what this actually does is, this swap in and out pages. So this is your RAM. I will discuss in memory management, but you have a lot of pages here, and when the memory becomes full, this medium term scheduler will basically kick out some pages from this to the disk. Similarly, it will also bring the pages from the disk to main memory. This is run by the medium term scheduler. And of course, if you see, there are links of a detailed video everywhere. So in those videos, I have talked about these concepts in very detail. And if you're interested, you can of course watch that. Now, of course, scheduling queues also I have already gave the example. So of course, job queue is there. That means tasks are waiting on the disk. This is used in batch OS. And of course, long-term scheduler is associated with job queue. Then you have ready queue. Now process waiting for the CPU are kept here. PCB of those processes that are waiting are kept here. Then this is short-term scheduler is associated with ready queue. Then of course you have another queue called device queue. Now you see, there are lot of devices there, right? You have keyboard, you have disk. In disk also you have like multiple disks. For each of this input output device, there is a separate waiting queue. So that is device queue. Now let's look into the next important part, that is context switch. So context switch is very quite simple, I will say. So what happens when one process is removed and another process is scheduled, context switch happens. So I will tell you the example here. This is your CPU, and let's say you have two processes, P1 and P2. Now they both have PCB also. This is PCB of P1, this is PCB of P2. Now, if you remember, in the PCB, a lot of information about process are stored. I mean, some information are program counter, register values. So do not confuse, I mean, register. So here also you will have register with CPU. I will tell you what the register values in PCB are here in terms of context switch. So what will happen normally is, so okay, let's say this P1 is picked first by the scheduler and it gets scheduled on the CPU. Now what will happen? Now this program counter, so this program counter is actually the next address of execution for the CPU. Now this will be basically put in one of the register here, let's say. And of course there are other register values also. Let's say, I mean, now we're assuming that P1 is getting a CPU for the first time, but that will not always be case. Let's say P1 was running before also. Okay, let's assume it is running for the first time. Okay, no issues. Now you put the program counter value here, right? And register value mostly will be empty because it is running for the first time. Now what will happen? It will run for some time, and in between, let's say because of scheduling algorithm, it needs to be removed from the CPU and some other will get time. So it will be removed from the CPU. But let's say it started at PC's program counter 0. Now it's, let's say, at program counter 100. So it is executing at 100 address of the its code. But now you need to save this context, right? Because P1 is going to get again some CPU time, right? So you need to save this. So first the kernel has to save this program counter update into this PCB, and then it can remove it from the CPU. And okay, it has to save other things also, because in between it would have used some register, right? Let's say it was executing some instruction, let's say A plus B, right? In that case, A and B values will be, let's say, stored in these registers. Now at this time context switch happened, so you need to also copy back these values also to this register. So that's why these registers are used, because next time again when this P1 gets time, you can directly copy back program counter again, and of course register values again, and I mean start the execution from that instruction itself. Now P2 will get time, and similar thing will happen now for P2 also. So you get what so this is context switch, because this context is being saved. So this context, if you see, was saved for P1 in this register values and PC. Now when P1 gets time again, this context whatever is stored here again will be put back here again, and it will start executing. That is called context switch. So CPU registers values are saved to the PCB of the removed process. That's what I did here. And so CPU register values are saved to PCB of removed process. So I was removing P1, so I saved all these values from CPU registers to these register values, I mean data that is present in PCB. And the register values from PCB of the scheduled process are loaded into the CPU registers. Now when this P1 gets chance again, I need to again basically load these values again first and then start the process. So this is context switch. And if you want detailed explanation, watch this video here in the link here. Now what is dispatcher? So dispatcher and context switch are both related. So what happens? Okay, the process scheduler has picked P1 for scheduling next on the CPU, but who will do this context switch and all, right? So that's the role of dispatcher. So if you see here, gives control of the CPU to the process selected by the short-term scheduler. So it will give the control of the CPU to this process. How it will do that? So it will do context switch. So I told you how context switch happens. You save the CPU register value to PCB register value, and the vice versa also you do. So that is done by this dispatcher. And also switching to user mode. So when some program wants to switch from kernel mode to user mode, that's also done by dispatcher. Now next one is non-preemptive and preemptive scheduling. Like what is the difference between non-preemptive and preemptive scheduling? So in non-preemptive scheduling, what happens? A process leaves the CPU voluntary. That means a process will only be removed from the CPU either when it terminates or it undergoes IO. So you cannot remove the process, like you cannot force the process from, I mean, you cannot forcefully remove the process from the CPU in non-preemptive. But in preemptive scheduling, there are other reasons. So of course these two are reasons, but there are other reasons why a process can be kicked out from the CPU. And basically that means you can forcefully remove, I mean the kernel can forcefully remove that process from the CPU. The reasons can be either the time slice of the process has expired, or a higher priority process has entered the ready queue, or maybe an hardware interrupt has arrived on the CPU. So in these cases, the kernel can or the scheduler can kick this process like which are running and schedule some other process that can happen. So they can interrupt in middle. The kernel can interrupt this process in the middle. In non-preemptive, that will not happen. A process, I mean that is if you have non-preemptive scheduling, a process will not be kicked out. It will voluntarily go off from the CPU if it wants, using only these two conditions. Now let's look at scheduling criteria, which is very important, I will say. So scheduling criteria means like, okay, what criteria you can use for scheduling. So let's say if you have 5 scheduling algorithms, how do you compare them? On basis of what you compare them? How do you say that scheduling A is better than scheduling B algorithm? How do you say that? So you can use these 5 parameters to judge scheduling algorithms. So first one is the CPU utilization, like how much time. So if you are using that CPU scheduling algorithm, in that how much time the CPU is busy, right? So let's say the CPU algorithm was running for 100 milliseconds. Let's say that's the example. Then out of this 100 milliseconds, for how much time the CPU was actually busy, right? If it was busy for 100 milliseconds, it's very good. But if it was busy for just 90 milliseconds, then for 10 milliseconds the CPU was lying idle. That may not be very good. Now next one is the throughput. The throughput is number of processes completed per unit time. So let's say, so you have, let's say, 1 hour time, and you are using scheduling algorithm, let's say A and B. Now for A, you are able to, let's say, run 10 process in 1 hour. For B, you are able to run only 5 process. That means the throughput for A is higher than throughput of B, right? That means A has higher throughput. That's what number of process completed per unit time. So here is 10 process per hour. This is only 5 process per hour. So of course A is better here. Similarly, you have other like turnaround time, is waiting time and response time. So understand this. This is very important. Understand the definition and also the formulas for this. This will help you in the numericals. So turnaround time in short form TAT is interval from the time of the submission of the process to the completion of it, right? So interval from when you have submitted the process for running till the process actually completes or terminates. I will tell the formula, you will understand better. Waiting time is total time spent by a process in ready queue. So do not confuse this. Waiting time is not the total time spent by the process in input output IO. That is, it is waiting. No, not that. Waiting time is total time spent by the process in ready queue. That means ready queue is basically those processes are waiting for the CPU, right? Some other process is running on the CPU, and these processes are waiting in the ready queue. So that's waiting time. Response time is interval from the time of submission of the process to receiving of the first response, or time spent by the process in ready queue for the first time. That means you have submitted the process now for running. It is in the ready queue now. So after some time, it will get the CPU, right? So the difference between those two times. Let's say at T1, you submitted the job, right? And at time T2, it got the CPU, right? So this T2 minus T1 is actually your response time. And some other important terms are arrival time or AT. So time at which a process arrives in the ready queue. This is very important. So this actually we tell the time of submission of the process when it arrives in the ready queue. Completion time is CT, time at which of course the process completes or terminates. Then you have start time, that is time at which a process starts its execution for the first time. I'm telling you for the first time because a process can, like in non-preemptive algorithm, a process can be like, it can run for 10 milliseconds, and this is your ready queue, let's say. It can be again kicked to the ready queue again. Again it will run for 10 milliseconds, again it will kick to ready queue again. So this will keep on happening. So a process will get the CPU multiple times. So start time is when it starts for the first time on the CPU, when it runs for the first time on CPU, that is the start time. Now burst time or BT is a total time spent on CPU or IO. So if it is CPU burst time, that means total time is spent on the CPU. IO burst time, that means total time is spent on the IO. By default, if it is BT is given, it should be CPU burst time unless it is mentioned like IO is there. In most cases, you will not see IO. In case if IO is there, they will mention it separately. IO burst time, CPU burst time, and IO burst time. Now let's see the formulas for this. So I told you what is turnaround time, right? The definition itself, I told you, interval between the time of submission and time of the completion. So completion time is CT and time of submission is of course arrival time. That is when it arrives in the ready queue. So CT minus AT gives you TAT. Now understand this. So TAT is basically the total time spent by the process. Once you have submitted the process and total time till it completes, right? That's what TAT turnaround time is. So basically you can also write that as total time spent in ready queue. So if you look at a process, what is the flow for it? Either it will be in the ready queue or it will be in the IO or it will be on the CPU, right? So you can write TAT as total time spent in ready queue plus total time spent on IO plus total time spent on CPU. That means TAT equal to WT plus BT, right? Because this is of course waiting time. As I told you, right? Total time spent in ready queue is waiting time. And this total time on IO plus total time on CPU is called burst time, right? Now, of course, do take care when you have IO, right? Because this burst, and normally you should write as WT plus IO BT plus CPU BT. But if you in most cases IO will be 0. If IO is 0, it will be only CPU BT. That's why I have written TAT equal to WT plus BT. This is actually total burst time. Remember this, right? When you have IO, do sum the IO burst time also. This is total burst time. Now, from this, you can always derive that WT is TAT minus burst time, right? We got the formula for WT also, for TAT also. And response time is quite simple. I told you, when the process gets the CPU for the first time, that means start time minus arrival time gives you response time. Then you have formula for CPU utilization and throughput also. So CPU utilization is total time, total scheduling time minus idle time, idle time when the CPU was idle, by total time into 100. This is in percentage. Throughput is total process by schedule length, and schedule length is given by this formula: maximum of all the completion time you have for all the process minus minimum of arrival time of all the process. So when I give the examples, you will understand better. Now let's focus on algorithms now. The first one is first come first serve, FCFS scheduling algorithm, right? So from the name itself, if you see, it's whichever arrives first, it will be scheduled first. That's what it actually means. The process which requests CPU first gets it first. Schedule according to the arrival time of the process. This is basically FIFO implementation. So you can use a FIFO queue and implement this. It's quite easy to implement. And it's a non-preemptive scheduling algorithm. So basically, it cannot be a process cannot be forcibly removed from the CPU in this case. Let's understand this with example. So if you see this example, I have three processes P1, P2 and P3 and their burst time is given. So if you see in this example, arrival time is not given, right? What is the arrival time of the process? But think like this can also be written as P1, P2, P3, arrival time, and I will just tell you arrival time is 0 for all, 24, 3, 3. So this problem can also be stated like something like this: arrival time is same for both. So when the arrival time is same for all the process, then always, so basically, always assume that in this case P1 has arrived first, then P2 and then P3. Sometimes they will tell it clearly in the problem that okay, P1 is arriving first, then P2 and P3. But if they have just given arrival time and all are 0, then also you should assume that P1 arrives first, then P2, then P3. Now let's try to solve this problem. So for all of these problems, we will try to draw the Gantt chart. So that gives the flow of like how the scheduling is happening. So if you see, as I told you, right, in this there is like arrival time is 0 for all. So P1 arrives first, then P2, then P3 arrives. This is given in the question. So at time 0, so we are assuming that time is 0, starting time is 0. Of course, I told you first P1 arrives, so it will get the CPU first. Till what time it will get? This is non-preemptive. So it will get till it completes. Total 24. Now this is completed. Now which will be scheduled? P2 will be scheduled. This is completed. Now P2 will be scheduled. Now P2 will be scheduled for bus time is 3. So it will be scheduled till 27. Right. Now this is P2. This will also terminate. The last process remaining is P3. Now P3 bus time is 3. So from 27 to 30 it will run. And your process scheduling completes, right? This is quite easy here in FCFS, and in some cases the arrival time can be different. Let's say 1, 4, 3, like this can also be given, but you can use similar approach. Basically you will see which arrives first. So in this case, if you see P1 arrived first, right? Arrival time was least for P1, so schedule P1 first. Then if you among P2 and P3, of course P3 arrival time is 3, so P3 will be scheduled second, and at last P2 will be scheduled. So always you can do this also. Now let's try to calculate these numbers. Now let's fill in the numbers. So I will fill in for 1-2 examples, not for all. For all, I will just draw the Gantt chart. You can fill in these numbers, and if you want to calculate the numbers, so basically for this problem you have to calculate average TAT, average waiting time, and average response time. You have to calculate, and also you have to calculate throughput and serialization also. Throughput and serialization. This is for all the problems I give here. You have to calculate all these 5. Now it's quite easy. Once you have this turnaround time for all these numbers, what you can do is you can find the average. It's quite easy, right, to do that. So I will do this for 1-2 problems. For rest of the problems, I will just draw the Gantt chart, and you can basically calculate these numbers. Now see, start time for process 1 is what? 0, right? At 0, process 1 is starting. For P2, it starts at 24. What about P3? It starts at 27. What is the completion time of P1? It completes at 24. About P2, it completes at 27. About P3, it completes at 30. Now if you remember the formula, TAT is CT minus AT. Waiting time is TAT minus bus time. And response time is start time minus arrival time. If you apply this formula, TAT is completion minus arrival. So arrival time for all is 0. That means this is 24, 27 and 30. Turnaround time will be same because starting time for all is 0. Now waiting time is turnaround time minus burst time. So turnaround is this and burst is this. So this will be 3. 27 minus 3 should be 24. And 30 minus 3 should be 27. Response time is start time minus arrival time. Now start time minus arrival time. So arrival time for all is 0. So this will be basically equal to the start time here. 0, 24, 27. Now if you want to calculate the average, you can calculate it easily. So average turnaround time will be sum these 3 and divide by 3. Average waiting time will be sum these 3 divide by 3. And average response time will be sum these 3 and divide by 3. You will get your answer here. Like what is the average turnaround time, average waiting time, average response time. Now for throughput, so if you see the total time for the scheduling was 30, right? And was CPU idle for any time? No, right? For all the time CPU was, executing some process. So it is for all the 30 time the CPU is executing into 100. So this will give you 100%. So this is not throughput, this is serialization. This is 100%. Now throughput is total number of processes that you have is 3 divided by scheduling length. So what is the maximum of completion time? It's 30. What is the minimum arrival time? It's 0. So it will be 3 by 30 or 1 by 10. It will be 3 by 30 or 1 by 10 your scheduling. So your throughput here. Now I will discuss 1-2 more problems. You will understand better. And if you want to practice more problems, these are links here. I have solved 3 problems here. You can practice this if you want. Now let's look into advantage and disadvantage of it. So advantage is, of course, it's quite simple to implement using FIFO-Q, and there is no starvation. So what does starvation means is, let's say if you have a process in ready queue which is waiting for the CPU, let's say P1, right? What can happen in some cases is that you have CPU here. In some cases what can happen, this P1 can wait indefinitely for the CPU and it will not get it. So it will wait forever, it will keep on waiting forever, and it will not be scheduled on the CPU. So basically it is starving of the CPU, right? So that's called starvation. So in FCFS, there is no starvation, right? Because whichever process arrives, right, in the FIFO queue, everybody will get time after some time, right? They will get the time of the CPU. Now, disadvantage is that waiting time can be very high here. So if you see the waiting time here for each process, for process 2 and process 3, the waiting time is quite high, right? So that can be the case here in FCFS. And also a convoy, this is really a convoy effect. So what happens in convoy effect is that a process with large burst time increases waiting time for the all the other process behind it. So think of like if you're in road, right? If you're in a road and you cannot basically take some, you can, so let's say this is the vehicle here, one, this is vehicle here, two, vehicle here, three. Now you cannot overtake this, let's say. Now basically this 2 and 3, this vehicle 2 and 3 are dependent on the speed of 1. So if 1 is very slow, then 2 and 3 will always be slow, right? So that's what is convoy effect. Similarly here, if you have process P1, P2, P3 in the FIFO queue, if P1 takes a lot of time, let's say 50 m, and for this the time is only 10. So the burst time for P1 is 50, burst time for this is 10, burst time for this is 10. But because this will take a lot of time, the waiting time for this and this increases a lot, right? So that's what is convoy effect. And also this favors CPU bound process over IO bound process, this FCFS algorithm. And also less throughput and serialization. And there is high waiting time here and very high response time. So because of that, there is very less throughput and serialization. Now let's look at a second interesting scheduling algorithm called SJF, or shortest job first scheduling algorithm. So in case I'm speaking a lot fast, watch this video at some lesser speed, because I have to complete a lot here in less time, so I may be speaking fast maybe. Now SJF is the process with least burst time gets the CPU first. So I told you FCFS was dependent on the arrival time of the process. Now SJF is dependent on the burst time of the process. Lesser the burst time, first you have to schedule that. So basically you have to schedule the first process will be the process which has the least burst time among all the process. And in case if the CPU burst time is same for two process, you can remove the conflict using FCFS. So let's say you have process P1, P2. This is arrival time, this is burst time. Burst time is 10 or 10 for both. Let's say arrival time is 2 and 1. So in this case, P2 will be scheduled first because for this arrival time is less. So that's what you have to do when the burst time is same. Follow the FCFS policy then. Okay, let's understand with this example. Okay, so I will draw the Gantt chart here, right? So I told you have to see on the burst time, but also you have to, arrival time is also given here. So you also have to look at arrival time. So at time 0, which all process you have, so you have to compare among them, right? If let's say you have the ready, okay, let me draw the ready queue here. Now understand this, if the process are in the ready queue, then only you will schedule them, right? So at time 0, which process are in the ready queue? Only P1 is there. So you do not have any options, you have to schedule P1 only, right? You don't have other process in the ready queue itself at this time, so you will schedule P1. And I forgot to tell you, I think SJF, I didn't tell you, okay, SJF is non-preemptive scheduling algorithm. So it will basically run till it completes. That means give all the burst time at the one go. So basically P1 burst time is 7, so it will run from 0 to 7. Now you are at time 7. At time 7, of course, if you see, all this process would have arrived here. P2, P3 and P4. And this one has already gone, terminated. But if you see at time 7, all these arrival times are less than 7. That means all these processes are already there in the ready queue waiting for the CPU. Now among these three processes, you have to select which one to run first. So of course you will go for burst time. Among these, which one has the minimum burst time? P3. So you will schedule P3. And since this is non-preemptive, you will give all the time from 7 to 8, right? Now this has, okay, P3 is gone from here. Now, so basically P1 and P3 are gone. Among P2 and P4, which has the least burst time? P2 and P4 both have equal. Now what I told, when two processes have equal burst time, what you will do? You will look at the arrival time. Now which has less arrival time? P2 has. That means P2 will get the CPU next. And P2 is 4 burst time, so 8 to 12. P2 is also gone, and the last only P4 is there. So just schedule P4. or 12 to 16. And I hope you can fill the numbers here again, right? If you want. Okay, okay. Let me just solve this one. This is only this. I will not solve the other problem. This is the last one. So look again carefully. So formula again. Let me just copy it. TAT equal to CAT minus arrival time. Waiting time equal to TAT minus burst time, and response time equal to, if you remember, response time was start time minus arrival time. So start time for process 1 is how much? 0. For P2, 8. P3, 7. P4, 12. Completion time for P1, 7. For P2, 12. P3, 8. P4, 16. You can fill these numbers now, right? CT minus 80. So 7 minus 0 is 7. 12 minus 2 is 10. 8 minus 4 is 4. 16 minus 5 is 11. Waiting time is TAT minus burst. So TAT is there, burst is there. This is 0. 10 minus 4, 6. 4 minus 1, 3. 11 minus 4, 7. So in case I do some calculation mistake, do correct it. And also do put the comments also that others can also see it. Response time is start time and arrival time. Sorry. So start time and arrival time. Start time here is 0. Arrival time is 0. This is 0. Start time is 8. Arrival is 2, 6. Start time is 7. This is 4. This is 3. 12 minus 5. This is 7. Now you can do the average of this all if you want. So basically your average, I will just give one example. TAT will be equal to 7 plus 10 plus 4 plus 11 by 4. Similarly, you can do average WT and average RT. Similarly, you can calculate the civilization and scheduling. Throughput and civilization here if you want. And of course, more examples of practice on SJF here. Now let's look at the advantage and disadvantage of SJF. So again, it's easy to implement. Like you have to basically sort in the, you have to look at the arrival time and the burst time and do it. It's not very tough to do it. And of course, here sorter jobs run first, right? Because of this, you have less waiting time. And if you calculate the waiting time here, of course, you will find it. If you see here, the numbers are quite less, right? If you do the average, if you see the waiting time has been less here, right? So normally in SJF and of course SRTF, the next algorithm, they minimize the waiting time. They provide the least waiting time among all the other scheduling algorithms. And of course, due to this, you have higher civilization and throughput than FCFS here. Disadvantage is that this can lead to starvation. So how it can lead to starvation is that, let's say you have like P1, let's say whose burst time is 100, right? Now what can happen if all the process after this, let's say P1, let's say first, okay, not let's say P0 arrived first, right, at time let's say 0, and for it the burst time is let's say 5, right? Now it arrived. Now at let's say time, now it will be scheduled, right? At time 1, this P1 arrives and it has burst time of 100. Now what happens is that after P0 arrives, P1 arrived at time 1. Now let's say it will keep running till 5, right? Now what can happen? It is running from 0 to 5. In between this, let's say a lot of process keeps on arriving on in the ready queue. Lot of process keeps on arriving, and they have shorter burst time than this P1. Right, all these processes have shorter burst time than this one. And let's say this keeps happening forever, right? Then P1 will never get the CPU, right? Because all the processes which are arriving are having lesser burst time than this. So they will get the CPU and P1 will starve of the CPU. That's why this can lead to starvation. Convoy effect is possible here also. How? Let's say at time 0, a process with large burst time arrives. Let's say 100 burst time arrives. Now, you understand what can happen. Now at 0, only this was there. Now at time 1, let's say some other process arrived with time burst time 10. At time 2, 10. But all these processes, this is non-preemptive. Now the first, this process will run from 0 to 100, and no other process can be scheduled in between. So this all process has a higher waiting time here. That's why convoy effect is possible here. And it's tough to implement, almost impossible to implement actually, because predicting the CPU burst time is quite tough. How do you know that, okay, for how much time the process will run, right? You do not know. So that implementing this is quite tough. This is easier to implement in code actually, but tough to implement practically in the, knowing the CPU burst time. Now let's move on to SRTF, the third algorithm. This is quite similar to SJF. The only difference being, so basically here also the same thing. You have to basically see the burst time and schedule. But difference here is, here you have preemptive scheduling. SJF is non-preemptive and SRTF is, sorry, yes, SJF is non-preemptive and SRTF is preemptive scheduling. Like both are same actually. Only difference is that one is preemptive and one is non-preemptive. Always remember this, which one is preemptive and which one is non-preemptive. Sometimes they can also call, also this can be called as preemptive SJF. You can also call this something like preemptive SJF also. Sometimes it can be called. Take the same example now. This is very tricky. So I will just listen here what I am saying. This is quite tricky. Preemptive cellular algorithm are not very easy to solve. So let's see this. Okay. Okay, sorry, why I'm drawing this big, sorry. So okay, at time 0 you do not, so this is a ready queue, let's say. Okay, now okay, I will not draw something like this. I will just let me keep this ready queue. Now at only you have P1 at time 0, so there is no other option, so schedule it from 0. Now at time 2 other P2 is arriving, so you can only schedule it time 2, because if P2 has lower burst time than P1, then you have to schedule P2, right? And you have to see the remaining, what is the remaining burst time, right? That is also important. So if you see here, this is 7, this is 4, and P1 is there, and it ran for 0 to 2, and this became 5 here, remaining burst time. That's why shortest remaining burst time, right? Now remaining burst time is 5. Now P2 also arrived. So P1 has not completed, P2 also arrived. Now at time 2, among P1 and P2, which has less burst time? That's why what happened actually, P1 got preempted and again it entered the ready queue after running. Right? I have not shown it here, but it again entered the ready queue. It got preempted. Now you are checking among P1 and P2. You see that P2 has lesser burst time than P1. So what you do is you schedule from 2 to 4. Sorry, this was P1. This is P2. This becomes 2 now. Right. Now why I am scheduling the 4 only? Because there are 4 other processes arriving P3. You need to check that also, right? Whether the burst time of P3 is lesser than P1 and P2. So now P3 is also there in the queue at P4. Now you have 3 processes, P1, P2 and P3. Among these, which has the least remaining burst time? Of course P3 has. It is only 1. So we do not, it is only 1, right? So we do not care about the next process P4. If it was 2 or 3, you also need to check P4. But okay, it's 1, so give it the time P3. And one good thing is that P3 has terminated. Its remaining burst time is 0. Right. Okay, and one more thing, I have removed it here, but always remember you will use that in calculation. So I have removed. So this is actually, actual value is 7, actual value is 4, because you will use in the formulas, right, when you calculate this, right? These all I will not calculate in this example, but you can do. Now of course P3 is gone here. Now at time 5, P4 has also arrived. Now you have all these 3 processes. Among these, who has the least burst time, remaining burst time? So this is done, 0, 5, 2 and 4. P2 is the candidate. Now P2 will get all the time. Why? Because you do not have any new process arriving in the ready queue, right? All the processes that are there are already there in the ready queue or have terminated. Now you need not to check for like, okay, because no process arriving at time 6 or 7, right? You not need to check that. Now give all the time from 5 to 7 to P2. P2 is over. Now you have P1 and P4. Among this is 4 and this is 5. Of course you will give it to P4. That is from 7 to 11. The last one is P4 is gone, P1, 5, that means P1, 11 to 16. And I told you, if there is some mistake here I am doing here, do correct me, right? So this is the Gantt chart for this, and of course you can calculate all these numbers if you want now. And this is quite tricky to solve because you have to always wait, like see for the arrival time of the next process, right, which is there, and wait and check the burst time again and do the scheduling. That's why preemptive scheduling is quite tricky. And you can practice a lot more problems here for like understanding more here what SRTF. What is advantage of this? Advantage is that again shorter jobs get first. I mean shorter jobs are scheduled first, less waiting time than the FCFS and SJF both in this case. Higher chip utilization and throughput than FCFS and SJF. And there is no convoy effect here because if you have process P1, that is 100 burst time, arrives at 0. Now if P2 arrives at time 1, right, having burst time of 10, of course this will preempt P1, right, because this has lesser burst time than this one. So this has remaining burst time at time 1, it will have 99 as the remaining burst time. This has 10. This will be scheduled now, so you do not have convoy effect. Now of course disadvantage is that this can also lead to starvation, as you can see, right. If a process with high has very higher burst time, it may keep on waiting, right, for the CPU. It's tough to implement again, similar to SJF. Predicting the next burst time is not quite easy. Okay, this is done, and the next two actually are quite similar to SJF and SRTF. So one is non-preemptive priority scheduling. So if you understand one thing here clearly, you will be able to solve SJF, SRTF priority scheduling. Like, so basically, if you understand SJF and SRTF, then solving non-preemptive priority scheduling and preemptive priority scheduling problems is quite easy. Understand this. So it's quite similar to SJF, non-preemptive priority scheduling. If you remember, SJF was also non-preemptive algorithm, but here priority is provided explicitly. That's only the difference. In the case of SJF, the priority was burst time, right? Basically, lesser the burst time, the more the priority was. So basically, the lesser the burst time, you have to schedule it first. That means the higher the priority was. Here, priority is explicitly provided in the problem. You will see, right? And it is given that, okay, if let's say, okay, I will go to the example and make you understand that. So let's say if the priority is from 0 to 127, let's say this number is given. Okay, do not assume that 0 is the lowest priority and 127 is the highest. It depends on the problem itself. In some cases, in some systems, maybe 0 is the highest and 127 is the lowest. In some system, 0 is the lowest and 127 is the highest. Both can happen. So always see what the problem is saying, right? It will always say which one is the highest, which one is the lowest. Of course, this is non-preemptive, as you can see here, non-preemptive. And in case of priorities are same, again follow the FCFS, similar to SJF and SRTF. In case the burst time was same in both other schedule algorithms, you need to follow FCFS. Similarly, here also do the same. It's quite similar to SJF. See this, I will solve this, and okay, there is no data here. Okay, there is no data here. Okay, I may forgot to fill in this. Okay, let me do one thing. Let me just do it quickly. Maybe let me just see it. And okay, I have the problem. I forgot to fill it. Okay, I got the problem. So the burst time here is 6, 12, 1, 3, 4. This is 2, 4, 5, 1, 3. I will send you the link actually from where I am solving this problem. You can solve a lot more problems from there. So let's try to solve this. Let's try to draw the Gantt chart. So each process basically, if the arrival time is not given, you will assume that all the process have arrived at time 0, and the order is that P1 has arrived first, then P2, then P3, then P4, then P5, right? So at time 0, this is non-preemptive if you remember, right? And okay, now you have to check. So all have arrived at a time 0, right? Now you have to select from the priority. Okay, here let's is given the lower the priority number, that implies higher priority. So I told you this will be always given in the problem, right? This will always be given in the problem. Like here I am telling that the lower this priority number, higher is the priority of that process. That means here 0 is considered the highest, and let's say some highest number, let's say 127 is considered the lowest priority that I have given here, right? So let's try to solve this. So among this, like which is the highest priority, you have to select the lowest among all this. So this is the lowest. That means P4 will be selected first. It will run from 0 to 3. Now this is terminated. Now among other, which has the lowest priority, sorry, highest priority or the lowest priority number actually, this one 2. So you will schedule P2. This is non-preemptive, so schedule till, I mean completely, right? Okay, sorry, P4 was burst time was 3, correct? P2 burst time is, sorry, now this is, no, this will be P1, not P2, right? It's 2, it's 6, so 3 is 9. Now this is gone, this is gone. Among 5, 4 and 3, this one. P5, burst time is 4 till 13. Among these two, this one, P2 first. P2, 12, 25. At last, P3, burst time is only 1, 26, and P3. This is done, right? From here, you can fill all these numbers and calculate. Non-preemptive is actually quite easy to solve. Preemptive is quite tough. So you understood this, right? How I took the priority here, right? I told you, right? The lower the priority number, higher is the priority. That means this one was the lowest among this. That means this is the process with the highest priority. That's why I told don't always assume that higher this priority number is higher the priority. Don't assume that. You will normally assume that okay, this is number 5. That means P3 should be the highest priority process. No, I have already told that lower the priority number here, highest is the priority. Always see the problem what they are telling. More examples can be found here if you want to practice more of non-preemptive priority. Let's look into preemptive priority scheduling. This can be, again, this is similar to SRTF, quite similar actually. Here, I mean difference here is that the priority number is given explicitly here instead of the, so there you will using burst time as the priority. Here the number is given differently. This is preemptive, right? So again, of course, SRTF was also preemptive. This is also preemptive. So let's try to, okay, fill in the numbers again here, same numbers. So it was bus time 6, 12, 1, 3, 4, 2, 4, 5, 1, 3, right? Let's try to solve this quickly. So, okay, I will again maintain ready queue here. Whenever I have non-preemptive, sorry, preemptive, whenever I have preemptive algorithm, I do maintain the ready queue. Now, okay, so all has arrived at time 0, that we know, right? So everybody is there in the ready queue initially. All the processes are there. Now among these, which has the okay, in this case, I think it will not matter much because arrival time is not there, right? So I mean, it will not happen that somebody will be, I mean, will be removed, right? In this case, because I mean, here everyone has arrived at the same time, so all are there in the ready queue at the same time. So basically, you can apply the non-preemptive version itself here, and it will work. But when you have the arrival time differently, maybe okay, maybe you can okay, maybe I will. What you can do is, okay, I will not solve any problem here for this. But if you, I think you would have understood SRTF, right? If you had understood this, I am sure that you will be able to solve this. But here burst time is, sorry, here arrival time is not given. So in that case, it means that, I mean, all are there, I mean, all are arriving at time 0. That means all are there in the queue at the same time. So it does not make sense to solve this problem because this will be similar to this one I solved before for the non-preemptive. So here are two examples here. Do try to solve the first one, I mean, and you will understand this, how this works actually. Do try to watch this video and you will understand. Okay, let me look at the advantage and disadvantage. So the disadvantage here is that advantage is that is very easy to implement. I mean, easy to implement in the sense that you can write the code, and it's good for critical process. So if you see, if you have some critical process, what you can do is you can increase the priority of that process, right? You can increase the priority of this process, and this will get scheduled first, right? That's why it's good for critical process. Disadvantage is that, of course, it suffers from starvation. I mean, all the priority scheduling algorithm, right, they suffer from starvation. but this can be solved using aging technique. So both of these priority scheduling algorithm that I discussed, for both of them actually these are the advantage and disadvantage. Both actually suffers from starvation, and it can be solved with the aging technique that I will discuss later. And it's deciding priority of the process is not quite easy. Like, okay, what is the priority of this process, right? Deciding them by the kernel itself is not quite easy here. Now, what is aging technique? So what can happen is, if you have low priority process in your, ready queue, they may be starved of the CPU, as I told you before, right? Now for solving this is only for priority scheduling algorithms, not for SJF SRTF. SJF SRTF cannot be you. You cannot use aging technique on that, right? Because those are based on the burst time. You cannot keep on increasing the burst time. Here, it's based on the priority. So what you can do is, okay, I will first discuss. Okay, and also there was a rumor that when they shut down the IBM this system at MIT in 1973, they found a low priority process that has been submitted in 1967 and had not been run. Right, this can happen, right? Maybe, okay, the priority of this was very low, right? And after this process, all the processes that arrived in the ready queue, they had priority basically greater than this. So this never ran actually. This is a rumor, but maybe true also. So what is aging is? Aging is a technique of gradually increasing the priority of the process that waits in the system for a long time. So let's check the example. So if your priority range from 127 to 0, so 127 is lowest priority and 0 is the highest priority. Now let's say you can apply this technique. So you can decrease the, let's say you have a process with priority 127. Now this is the lowest priority here, right? As I have mentioned here, this is the lowest priority. Now what can happen is, after this process, what can happen, all the process with higher priority arrives, then this will never get the CPU. Now what you can do is, every 15 minutes decrease the priority of this by 1. So every 15 minutes you will decrease this, so it will become 126. After 30 minutes it will become 125, and after some time, let's say it will be, let's say 1 day or 2 day, it will finally become 0, right? And 0 is the highest one, so of course this will get scheduled, right? So aging technique, using aging technique, you can basically prevent the process, low priority process, from starvation. Okay, let's move on to last one, round robin scheduling algorithm. So this is mostly used in time sharing operating system. Okay, I will explain why. So this is basically combination of FCFS and preemption. So in FCFS, if you remember, there was no preemption. Here in round robin, of course, FCFS is followed along with preemption. So how the process are preempted is actually, they are preempted, they're preempted. So basically they are based on time quantum or time slice. This can vary from 1 to 100 millisecond. So when I take the example, you will understand more. And this is implemented using FIFO-Q. So what happens in time? So I told you time sharing of system because, let's say, time quantum is 4 millisecond. So process P1 will run for 4, and it will be removed from the, so it will run for P1 4, it will remove from the CPU. P2 will run for 4 again, this will be removed from the CPU. P3 will run for 4, this will be removed from the CPU. But again, let's say only these are 3 processes. Again, P1 will again run for 4, again removed. P2 so this is round robin. You get it right from the name. This is round robin, right? This keeps on happening in round robin fashion. Okay, better to understand this example. Here you have arrival time, burst time given, and time slice or time quantum is given 4. That means after 4 millisecond, you have to remove that process. So initially, let's draw the queue here. This is the ready queue here. So at time 0, you have only P1. So let's give, you can maximum give till time quantum. You cannot give max than that. So here burst time is 8, but you can only schedule that till time quantum, that is 4. Right. Now at time 4, many other processes will, so all these processes will also arrive, right? So P2, P3 and P4 are already there, right? Already there in the ready queue when you have completed P1. Now what P1 has some burst time remaining, right? The burst time remaining is 4 here, right? And 4 is already done. So what you will do is, you remove from the front of the queue and push it to the end of the queue, right? So it will get time after all this which are waiting in the queue completes, then P1 will get time. Now next one in the queue is P2. So you get P2 here. Now P2 burst time is exactly 4 and time quantum is 4. So it will complete like all the burst time here till 8, and this will basically P2. You can kick this out from the ready queue. It has terminated. You can kick it out, and P2 is done. Now next one in the queue is P3. P3 has 9 as the burst times, but it will get only 4, 8 to 12. So basically from 9 it has the remaining ones is 5. And now remove it from here, push it at the end of the queue. Now you have P4. P4 burst time is 5, but it will get only 4. Remaining is 1 for it, and kick it to the last. Now you have P1. P1 remaining is only 4, so give it all 20. Kick out P1, is terminated. Next P3 in the queue. P3 has 5 remaining, so this will reduce to 1 now from 5. P3 from 20 to 24, and P3 will be pushed to, like, now new queue will basically will be P4 and P3 here. Now P4 has 1, give it 25. This will terminate, gone. P3 has again 1, give it till 26. This is also gone, and this is scheduling, right? Now you understood, right, what I did here, right? I only schedule this process if it has, like, bus time was 8, I only gave it 4 bus, I mean bus time of 4, and I'm using FIFO queue here because time quantum is 4. I'm giving only 4 units of time here, right? And more examples here for round robin again if you want to practice. Advantage is that it has better response time. Why? A response time, if you remember, was like how much time the process waits in the ready queue for the first time. Now it doesn't have to wait much, right? Because after 4, 4, 4, and every process will get chance, right? That's why response time is quite great here. There is no starvation here. You have round robin. In FCFS, there will never be a starvation, right? Because you are going to pick from the queue and keep on scheduling. No convoy effect here because everybody gets time, right? I mean, even if let's say the 100 is the burst time for first process, it will only get 4 units of burst time, right? So you do not have convoy effect. Disadvantage is that, I mean, convoy effect can be there if this time slice is quite high. If time slice is, let's say, 100 itself, then convoy effect may be there. Disadvantage is that average waiting time is very high here, because if you see, everybody gets 444 round robin, again 444 round robin, right? So all the process, they keep on waiting in the ready queue most of the time, right? And there is also issue with this. If you keep the time slice or time quantum very low, then there will be frequent context switch, and context switch itself takes some time. And if the time slice is high, then it will almost become like FCFS in that case. Okay, these are the 5 most important scheduling algorithms, but I will also discuss the theory for multi-level scheduling algorithm. So in this, what happens here, ready queue is divided into multiple queues here. So you see here there are multiple queues here: system process queue, interactive process queue, interactive editing process queue, batch process queue, student process queues, right? So this system process means all the kernel process will be here. Interactive process means all your IO bound process will be there. I mean, your text editors and everything, those are interactive, right? The applications with which you interact will be placed here. Interactive editing is subclass of interacting. I mean, editing means text editor will be here. Batch process are like, okay, like they run in background, right? So those are batch process, they will be kept here. And this is student process. And also among all of this, right, for each of this, like each of this queue will follow its own scheduling algorithm. So this queue can follow, let's say, FCFS. This can follow priority. This can follow maybe round robin, right? It can happen. And again, all of these scheduling queues also, like they will also be scheduled in some order. Like let's say if you are using priority scheduling, let's say this is the lowest priority and this one is the highest priority, right? So you will follow that. Okay, read here. So each queue has absolute priority over lower priority queues, right? So no process in the batch queue, for example, could run unless the queues for the system process, interactive. So basically, no process in student process can run. So basically, no process in this queue will run until all these queues are empty, because this is the lowest priority one, right? This queue. That's why. Similarly, if an interactive editing process entered the ready queue while a batch process was running, the batch process will be preempted. This is basically among these all queues you are following. So within these queues, you are following some algorithm. But among all these queues, you are following preemptive priority scheduling. That means, let's say if you are in this student process, some process is executing here P1 in student process, which one is of the lowest priority, and some process P2 arrived in the system process queue, then P1 will be preempted and P2 will run. That's what it means. So another possibility is to use time slice among the queues, right? So we are using preemptive priority, but you can also use round robin. Here, each queue gets a certain portion of CPU time, which can divided between the multiple processes within that queue. For instance, in the foreground background queue example, the foreground queue can be given 80% of the CPU time for RR scheduling among its process, whereas the background queue receives the 20%, right? So 80% of the time you give to foreground, let's say queue, and 20% to the maybe the background queue, right? And this time will be split between all the process that are in this queue. This time will be split between all the process that are there in this queue. Then you have at last multi-level feedback queue scheduling. So in multi-level queue scheduling, processes are permanently assigned to a queue. So as I told you here, right? All the processes are fixed. Like some processes will go here, some will go here, right? They cannot change in between. So, but this feedback scheduling algorithm, actually, this algorithm allows process to move between queues. In between, they can move between the queues. That's what's the difference here. So basically, the idea here is to separate process according to the characteristic of their CPU burst. That means if a process uses too much CPU time, it will move to the lower priority queue. And this seam leaves IO bound and interactive process in the higher priority queue. So basically, here the scheduling is dynamic. So depending on the CPU burst time, one process can be kicked out from one queue and placed into other queue. That can happen here. And also, in addition, a process that waits too long in lower priority queue may be moved to a higher priority queue. In order to prevent the starvation case there, right? That can also be done. So this is quite dynamic algorithm, right? So basically, this is similar to this, but in this is like a static algorithm, right? Once the process has been assigned to one queue, they cannot be moved. Here, they can be moved based on the feedback of the CPU burst time. Okay, I think that's all for this video. And for all the numericals that I have solved here, here the link is not there, but once I attach it in the video description, you will see the solutions to those problems also in that. So I think that's all for this video, and do provide your feedback on this this video, this session, and also do not forget to subscribe to my channel and also watch my other videos on the same. Thank you.